In this video, we'll be using the law of sines to solve our case 2 type oblique triangles. That case 2 type triangle is when we're given the lengths of two sides and the angle opposite one of the sides. It's not the angle in between the two sides. When we're given this side-side angle situation, it's possible for 0, 1, or 2 triangles to exist. Please note that when we discussed the congruence axioms for triangles, there was not one for side-side angle. So let's talk about why this might occur, the 0, 1, or 2 triangles. So suppose we know the measure of an acute angle A of a triangle and the length of side A and side B. So that's our case 2 given. An angle and then sides and the angle's not in between the two sides. Right. So what I'm going to do next is we need to draw the side of length A opposite length A. Right, so that's this one here. It's kind of dangling. It looks weird like that because for each problem, the length of side A is going to differ. So sometimes it reaches this other side and creates a triangle, and sometimes it doesn't. So that's why the diagram kind of has it weird dangling like that. The key to determining the number of possible triangles, 0, 1, or 2, lies primarily with the height of our triangle. See, check this out. The shortest possible distance from our angle C down to this third side is a straight line. We know that's the shortest distance between any 2 points. So the shortest possible length for that side A, which is highlighted in green, the smallest it could possibly be, has to be equal to H. It might be bigger than that, but if side A is smaller than that, then it's not going to close and create a triangle. And it is true that H is equal to B times sine of A. So where are we getting that? If we look at, I got so much highlighting going on here. All right, if we look at this triangle, it's a right triangle, so we can use SOHCAHTOA, and from angle A, H is opposite and B is our hypotenuse. So sine A is equal to H over B. And if we solve for H, we get B sine A. That's where that comes from. Okay, so our first situation is if that H that we found, which is the height, the shortest distance between our angle and our side, if our height is greater than A, then no triangle is going to exist because that side A isn't long enough to touch the bottom. Now, if H and A are exactly the same, then a single right triangle exists because it's the shortest distance. There's that perpendicular at the bottom. Now, if the height is less than A, so our side A is longer than the height, 1 or 2 triangles may exist. And the reason for the option there is because we don't know what angle C is, we don't know how that third side swings. It might swing this way and touch the bottom and create this triangle, or that side A, maybe it goes down here, because remember, we also don't know the distance of the bottom side, so it's possible that it's long like this, and then we would have this big triangle here. So there might be one option, there might be multiple options. This situation, because of all these options, is called the ambiguous case of the law of sines. You're going to hear ambiguous case way more than you're going to hear case 2 law of sines. So we don't have to rely on an illustration to draw the correct conclusion in the ambiguous case. We can apply the law of sines to the values of what we're given, A, B, and capital A. Of course, those variables might change from example to example. And use some basic properties of geometry and trig to determine which situation applies. So we're going to be using these following basic facts. For any angle of a triangle, sine of that angle has to be between 0 and 1. And we're only choosing positive there, right? Because we're talking about angle measures inside a triangle and lengths of sides. If sine of theta is equal to 1, then our angle is going to be 90 degrees and we'll have a right triangle. Number 2 says sine of theta is equal to sine of 180 minus theta. That is, supplementary angles have the same sine value. We've already been using this a lot for things, and we're going to continue to use it a lot here. I guess maybe we just didn't state it exactly like this. See, when we were using inverse sine and finding sister triangles, right? Maybe we had one here with a reference angle of 20. Sine is positive in quadrants 1 and 2, so then we'd say, oh, there's another one over here. And the way that we actually got the angle measure for over here was we took 180 and we subtracted the 20, which was the reference angle. That's what this property number 2 here is saying. So we're going to use that a lot with these law of sines. And the smallest angle is opposite the shortest side, largest angle opposite the longer side. And we've been doing that as well. What I typically do with ambiguous case, and I know it's going to be ambiguous case because I'm given a known pair, so I know it's sine, law of sines, and I know it's ambiguous case because I'm only given one angle. I just always assume that there's more than one triangle, and if there's 1 or 0, it will clearly present itself to us. And don't worry, I'm going to do examples so you can see what that presentation looks like. So let's determine the remaining sides and angles of the triangle, and we'll round our answers to the nearest hundredth. I see side C and angle C, a known pair. So I know I can do law of sines here. I also notice that only one angle is given, so this is going to be the ambiguous case, and I'm going to have to, kind of be heads up for that. So side C over sine of angle C equals side A over sine of angle A. And we need to solve for angle A. We have a proportion, so we'll cross multiply. Sine of A is equal to 2 sine of 50 degrees. Since we're solving for an angle, we're going to have to use an inverse trig function here. Angle A is going to be sine inverse of 2 times sine of 50 degrees. And we're going to plug this into our calculator. Make sure you're in degree mode, and we'll round to the nearest hundredth. Plugging it in, what does your calculator say? Go ahead, try it again. We're getting an error from our calculator. See, we're getting an error from our calculator because this value right here, 2 sine of 50 degrees, is larger than 1. And our first property up here said that sine of theta has to be between 0 and 1. And that's what we're taking sine inverse of, so that's why we're getting an error. Now I don't think about this property up here. I don't try to figure this out and plug that in and stuff. I just plug it in my calculator, and if it says error, then we can conclude no triangle exists. So this is the situation where side A is too short to be able to reach the third side and close up a triangle. Let's try another one. Here, side A equals 6, side B equals 8, side A equals 35 degrees. We know it's going to be law of sines because we have a known pair, and we know it's going to be the ambiguous case because only one angle was given. We get 6 over sine of 35 degrees is equal to 8 over sine of B. And we cross multiply. 6 sine of B equals 8 sine of 35 degrees. Continuing to isolate our sine, we'll divide both sides by 6. Sine of B equals 8 sine of 35 divided by 6. You could simplify that fraction if you wanted, but I wouldn't since I'm just going to plug it in my calculator. And inverse sine to get our B. B is going to be sine inverse of this fraction here. And we're going to plug it into our calculator. When we do that, we get not an error, we get a number. Remember, we're rounding to the nearest hundredth. We get 49.89 degrees. And that's a great answer. But I don't know if this is going to swing one way or another to create 1 or 2 triangles. So I always assume that there are 2 triangles in existence. Now, we're going to use this fact 2 here, that sine of theta equals sine of 180 degrees minus theta, to get the second angle, the second possibility. All right, so we're going to do possibility 1 and possibility 2, and I'm going to use subscripts to distinguish between the two. So we're saying that angle B for possibility 1 is 49.89 degrees. Now, since you didn't get an error in your calculator, when you put this in, you know for sure you have at least 1. It's just now determining whether we have a second one. All right, so in the possibility that we have a second one, our angle B would be the supplement of this because of that property 2 above. And when we subtract, we get that B2 would be 130.11 degrees. All right. Let's go on to finding our third angle A, because right here in this step for these two parts 1 and 2, this is where we're going to determine whether there's just one triangle or 2 triangles. Angle C, we know that the 3 sides of a triangle have to add up to be 180 degrees. To find our third angle, we're going to take 180, subtract A that was given, and then subtract B1 that we figured out. And again, you should always get an answer for this one. It's the second part that's a maybe. Oh, we're going to get 95.11 degrees. We're going to do the exact same thing with the second triangle. To get the third angle, we're going to take 180 degrees, subtract the angle A we were given, and then subtract the angle B that we found here in the second case. When I do that, if I get a positive number, then a second triangle exists. And here we get 14.89 degrees, so we are going to have this second triangle here. If angle A and angle B together are already more than 180 degrees, you're going to get a negative answer, and that's why we couldn't possibly have a second triangle, because there's no way that the sum of the interior angles can be more than 180 degrees. But since we got something that wasn't a negative, that tells us for sure 2 triangles. All right, last thing we need to do is find side C for both of these situations. To find our side C, we're going to use our known pair, 6 over sine of 35. And that's going to be equal to our side C1 over sine of 95.11 degrees, and we'll cross multiply to solve. 6 sine of 95.11 equals C1 times sine of 35. And then we'll divide and get that C1 is 6 times sine of 95.11 divided by sine of 35. We'll plug this into our calculator. Rounding to the nearest hundredth, C1 is 10.42, and our unit is yards. We need to do the exact same thing with our second case triangle. We'll start our proportion with our known pair, the one that was given, and then that's going to be equal to side C2 over sine of 14.89 degrees, cross multiplying. We get 6 sine of 14.89 degrees equals C2 times sine of 35 degrees, and then we'll divide. C2 equals 6 sine of 14.89 divided by sine of 35. Plug that into your calculator and round to the nearest hundredth. We get our second side C to be 2.69 yards. All right, one more application. I know the video is long, so if you need to take a pause and then come back to the application, then do that. All right, last one, application. After a windstorm, you notice that your 16-foot flagpole may be leaning, but you're not sure. From a point on the ground, 15 feet from the base of the flagpole, you find that the angle of elevation to the top is 48 degrees. Is the flagpole leaning? If so, find the acute angle to the nearest degree that the flagpole makes with the ground. All right, well, the first thing we need is a picture. Here's my ground. Let's assume it's like perfectly straight, which it is definitely not. Let's try again. All right, and then I have a flagpole that may be straight up and down, maybe leaning. I think when I draw it, I'm going to make it a little bit leaning. All right. It's important to be patriotic. All right, so it tells me that you notice that your 16-foot flagpole, all right, so this is 16, from a point 15 feet from the base of the flagpole, so over here 15 feet, you find that the angle of elevation to the top is 48 degrees. And we want to know, is our flagpole leaning? Well, how would we know if it was leaning? If our angle right here that the flagpole is making with the ground is anything other than 90 degrees, then our flagpole is leaning. So if we can figure out what that is, we're in good shape. We can answer our question. All right, well, let's look at what we're given. Notice that we have this side 16 and the angle across from it, 48. Since I have a pair, that tells me law of sines is appropriate. The other piece of information I was given is that this number here at the bottom, which you can't see because of my grass, this number here at the bottom was given, and with law of sines, things are paired up. So we could figure out what that angle would be. Now, why is that helpful in helping us determine whether it's leaning? For our angle at the bottom to be 90 degrees, it means that these other two, the yellow and the blue one, they have to add up to be 90 degrees to force that one to be 90 degrees. So if we figure out this and find it to be anything other than complementary to 48 degrees, we're leaning. All right, let's set up our law of sines. We'll call this angle theta up here. 16 over sine of 48 is equal to 15 over sine of theta. It will cross multiply. And then we'll divide by 16. And to figure out theta, we'll need inverse sine. Theta is going to be sine inverse, so this fraction here. Plugging that into our calculator, and we'll round to the nearest hundredth. We get theta to be 44.16 degrees. Since this is the ambiguous case, it is possible that we have a second triangle. So we really do have to go through our second triangle test. To get our second triangle, or our second theta, theta 2 is going to be 180 degrees minus theta 1. So theta 2 is going to be 135.84 degrees. To get the third angle at the bottom, I don't know, call that alpha. This alpha 2, remember we find that by taking 180 minus the angle that we were given, which was 48, minus this theta 2. And if we get a negative number, then we know that a second triangle is not going to exist. So when we subtract these, we get this alpha 2 to be negative 3.84. So that means a second triangle is not going to exist, and the only one we need to worry about is this 44.16 degrees. All right, let's get back to answering the question in our application problem. So the question is this flagpole leaning? So to determine whether it's leaning, that means that our angle theta here has to be complementary with the 48 degrees, and it's not. When we add those two together, we get 92.16 degrees. So that means that we're leaning. And it asked, what's the question here? If so, find the acute angle to the nearest degree that the flagpole makes with the ground. Well, 92.16 is not acute. Remember that acute has to be less than 90 degrees. So to get that acute angle, we're going to subtract from 180 degrees. Right, really what we're finding is this angle. So let me put my grass back. Really what we're finding is this angle right here. 180 degrees minus 92.16 degrees. Our flagpole is making an angle of 87.84 degrees, with the ground rounded to the nearest angle, 88 degrees.